Good morning and welcome back. This morning, I have sent a file, an email, a notification to you to inform you the change of our course. Let me briefly discuss the change. The major change is we will use a distance learning mode due to COVID-19. So I will upload the file to YouTube so you can learn by yourself. I will upload the file soon, hopefully. Okay. The second change is our final oral presentation will be, you don't have to come to class, just record the video file and upload to YouTube 15 minutes video files and up to YouTube. Or you can send the file to our TA, Tsun-Hsu Chang. He will collect all the presentation file. And then we will evaluate the papers, the presentations. So we don't have to collect in the classroom. Second, let me show you. That is the change here. The schedule. Okay. Today is May 19th, and we still have 4 weeks to go. I will finish chapter 6 in 2 weeks, and then I will talk about special topics, electron spectral measure, gain and bandwidth, closely related to our course. Okay, that's the change of our schedule slightly. Go back to today's course. Today we will finish. No, we still have roughly about 60 something to cover, and we will discuss the linear velocity of waves in magnetized plasma. Here, pay attention. Magnetized, that is with B field. In a previous case, we just discussed without the B field, but now we will discuss with the B field and see what will happen. As our usual case, let's go back to the very beginning of part 2. Okay, we will. This is the general theory of linear velocity of waves. In this case, we will discuss here magnetic field. This is very useful, very important. For example, our first special topic, the electron spectral measure, ECM, well related to this case. Second, the gain and the bandwidth. We will talk about another case, omega-kz relation. Gain and the bandwidth allow us to calculate this case, omega-kz. So how to deal with a problem like that? So first, let's have a equilibrium, zero order solutions. So equilibrium, if we have a velocity distribution, zero order, and obviously this is the velocity equation. This part do not related with time, so correct. And this one is space derivative, also correct. And we assume no electric field, no external electric field. So this one correct. Therefore, this one must be 0. This part must be 0. That is this one. Under what condition this function, this distribution function will be 0? Here is an example. If we can separate into two parts, the distribution function depends on perpendicular velocity and z separate into two parts, then this function will always be 0. Okay, you can imagine. So here is some special case. For example, the Maxwellian here. Maxwellian, by Maxwellian, or this one. Actually, we will use this one. Okay, we will use this one. So the distribution function, as well as this one as well. And we can separate the perpendicular and VZ velocity length. The 0th order velocity equation will be correct. Next, let's consider the first order equation. Velocity of Maxwell equations. These 5 equations can be written as this form. This is the velocity equation, distribution function. And we know 0th order is here and first order is here. E-field, because E0 is equals to 0, but B0 is not. And so we have B1 term, E1 term. And for rho 1, J1, they are related through the conservation of charge. This process is called linearization. So the velocity equation now still have 5 equations. Linearize. This related to first order, and to the right hand side, 0th order. Okay, Maxwell equation here, second, third. Okay, rho and J are related through these relations. They can be calculated if we know the distribution function, if we know this one. Okay, this one is particle dynamics. Let's examine the particle dynamics. Partial TFR1 plus this one. That's the equation we just have. So left-hand side is closely related to F alpha 1. Alpha is species alpha. If we have one species, for example, electrons, then this one will be very easy, just one species. If we have 2 species, we have electron and ion, then they have 2 species. And this one can be simplified into this one. And right-hand side is here. Okay, so if we want to calculate this one, we need to know V, the velocity. We want to calculate this one. We need to know the velocity as well as position. Otherwise, it will be very difficult. So this is the knowledge we obtained from chapter 2 for the sectoral motion. So the sectoral motion, we separate into perpendicular component and Z component and perform. This is the sectron frequency related to B0, Q, B0, mc. For electrons, you can write into E B0 over MEC. Okay, the spectrum frequency roughly about 1 Tesla correspond to 28 gigahertz. That's the spectrum frequency. Okay, just give you an idea. 1 Tesla is about 10 to the 4th Gauss. Okay, very strong magnetic field. So if you want to generate one terahertz, then you need roughly about 40 Tesla. That's extremely strong magnetic field. Okay. So we should express velocity and position through our knowledge, the knowledge we have before, and substitute to equation 117. Equation 117. Okay, and we can perform the integration, change to the variable, and perform the integration. So we can derive these relations, this one, into 2 parts and integration. But up to this point, it's still not easy to calculate. We will consider normal mode. Also, it's a separation of variable. We just separate time dependent, space dependent, and velocity dependent. Separate them. If we can deal with, let's just assume, we just consider this case, normal mode. If we do not consider normal mode, obviously it will be complicated. But we normally consider normal mode. Our purpose, remember, our purpose is to find a relation between omega and kz. That's our purpose. Our purpose is to find a relation between omega and kz. That's the so-called dispersion relations. Okay, so normal mode is quite common. It's just like a separation of variable. Substitute this one. So equation 117 becomes equation 119. And we can further separate into, by change the variable, prime and unprime system, separate them. So that's the left-hand side. That's the new right-hand side. We have something in common. Looks like if we can factor out, then this one can cancel. And it's possible because it's related to very, very long ago. It's possible. So this part can be 0. I will show you quickly. And in that case, we have a common factor. We can factor out the common factor. So we can simplify the calculations. Okay? Under what condition this term will be 0? This term will be 0. Go back to this one. This term. Yes. Prime. Okay. Under what condition? Like this part. If the omega is a complex and the imaginary part is greater than 0, then let me write this equation again. Exponential minus I omega r t dot exponential minus I times I omega I t. So this part gives us exponential omega I t. If t minus infinity, this one will be 0. Okay, maybe very small. So this equation can we factoring out exponential dependence, no more dependence. So we have a simple structure. Great. That's equation 1, 2, 3. And we know rho and J are correlated. Rho can be found from the knowledge of J here. Okay, so no problem. And omega I at this moment we assume is greater than 0, but because of analytical continuation, actually omega can be arbitrary. Omega R plus I omega I, but omega I can be positive, can be negative. So we already deal with a problem like that before. And zeroth order can be a constant of motion. Sector motion. This is mass of characteristic or integrating over unperturbed orbit. What is unperturbed orbit? Unperturbed orbit is gyrating electron under magnetic field, under B0. Okay, how about the field equation? The field equation from the linearized Maxwell equation. This is the Maxwell equation with Helmholtz, this one, what's this one? This is the Faraday's law. This is the Ampere's law. Okay, we know how to calculate J because we can integrate. We have a constitutive relation. J1 will be related to F alpha 1. Perform the integration. Okay, remember. Okay. And how about E field and B field? They also related through a simple relation. If we perform curl of this one, curl of this term again, and curl of B1. So everything is related to, we can change to this form. Okay. This one, E1 is related with K and J1K. Okay. So we have two equations. Go back to this one. Okay. And section 6.11 is linear velocity of waves in unmagnetized plasma. B0 equals 0 in the previous section. But now we will focus on magnetized plasma. So dispersion relation. Let's calculate the dispersion relation. That's omega kz. And we began this section with the derivation of the general dispersion relation for waves in an infinite, uniform, and magnetized plasma on the basis of the following linearized equation we just derived, and we use normal mode exponential minus I omega t plus ik dot x dependence. So from these relations, we have two equations. From the previous derivation, to calculate f1k, you need E1 and B1k, but E1 and B1 are related, okay? And you need to know the zeroth order distribution, okay? And E1, E1k and J1k are also related to these properties. Okay, how to deal with a problem like that? Think about it. In the next 30 pages, I hope you don't focus on the mathematical details, because from my experience, most of the students have the ability to derive this equation by themselves if we give him or her some example to follow. So don't focus on the mathematical detail. Look at the big picture. Just have an idea how to deal with a problem like this. Okay, in that case, you will change your mindset. You just enjoy the beauty of the techniques from different viewpoints. Okay, let's enjoy the beauty of the techniques. This will give us a lot of information. When we assume a uniform magnetic field and show that equilibrium distribution function is that. That's equilibrium function. So the plasma is isotropic in the SY dimension because B0 is in a G dimension, but it's a three-dimensional anisotropic. On a three-dimensional viewpoint is anisotropic. Thus, we expect the conductivity J1 is related to, it's a three-dimensional problem. J1 is related to these relations. Okay? Related to these relations. This one related with J and E1K. So that's the strategy. This is the conductivity. It's no longer a proportional constant. It's a tensor. It's a conductivity tensor. Sigma is a conductivity tensor. Let's have a look. Just imagine the general form of the dispersion relation. J equals this one, and E1kx, E1ky, just use Cartesian. T-E-S-I-A-N, Cartesian coordinates. Okay, SYZ coordinate. And without loss of the generality is 共通性，没有失去共通性。For a plasma isotropic in X and Y, we can let K is a propagation constant, separate into two parts, S component and Z component. Of course, you can use EY component, and the result will be similar. here we just assume it in EX component for our convenience. EX component. Okay, we make this assumption and we substitute K to here. And we know J is related to here. So left-hand side is related to Ks E1 KX component, E1 KY component, and E1 KZ component. Okay, and the left-hand side, the right-hand side, we can just write it down. And we can change. So this one separate into 3 parts. Yes, E1KX, E1KY, E1KZ. This one gives us E1KX times sigma XX here. E1KY times sigma SY and sigma XZ plus X component E1K. This will give us omega over C. And maybe we should factor out some coefficient. Omega over C, so divided by C omega squared, C squared. So cancel, 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 cancel. Therefore, we have omega here. Yes. Yes, the coefficient is correct. And here divided by 1. And we still have other terms. So X component give us this one. What else? No. And Z component give us this one. So we have 3 equations. 1, 2, 3. And these 3 equations can be rewrite. Have a closer look. Have a close look at this one again. E1KX, E1KY, E1KZ, E1KX, E1KY, E1KZ, E1KX, E1KY, E1KZ. Okay, pretty good. So we can rewrite into a new tensor. We can rewrite this equation into this form. Into this form. D actually is sigma plus something, right-hand side, left-hand side. So what is the equation of D? Here, that's the detail of D. Of course, at this moment, sigma XX, sigma SY, sigma XZ, and we have 9 components is still unknown. So later, I will show you how to derive this 9 components. Actually, can be derived from here. Can be derived from here. Because J can be calculated from the distribution function. And distribution function is related to this one. So eventually we can find a relation between J1K and E1K. That's the conductivity tensor. Okay, so from equation 147, 148, this one or this one. This one to be solvable, the determinant D, this tensor must be 0. Otherwise, we have trivial solution. So determinant of this one must be 0. That's equation 149. 149 is the most comprehensive form of the dispersion relations. So for magnetized plasma, magnetized plasma, M-A-G-N-E-T-I-Z-E, M-A-G-N-E-T-I-Z-E, magnetized plasma. We can start from this equation. Okay, actually, this one. That's the determinant equals 0. The detail will be to calculate this one. You need to calculate the distribution function. Again, calculate the distribution function. But to calculate this one, you need the knowledge of V. You need to know its position. You need to know the position. Therefore, we need a particle dynamics, particle trajectory, zeroth order trajectory, unperturbed trajectory, spectrum frequency, spectrum behavior, gyrating around the magnetic field. So we just write into this form. That's the particle dynamics. Particle dynamics give us the information of the V prime and X prime is vector. Okay, so with this V prime and X prime, we can calculate F. We can calculate this one. Okay, with this one, we can calculate J1. And J1 will be related to E1K. So we can calculate, our purpose is to calculate sigma conductivity tensor, C-O-N-D-U-C-T-I-V-I-T-Y conductivity tensor. Okay, that's our purpose. The mathematics looks complicated. If you do not have an experience, that mathematics is really complicated. Therefore, I do not expect you to fully understand what's going on. I just expect you to have the picture, have the big picture, not the detail. Have the big picture about the magnetized plasma. So when you deal with a magnetized plasma, you can come back to the lecture note and you will have a better understanding at that time. I will send you 2 papers. We will use this idea and calculate almost everything. Okay, so here, K divided into S component without loss of generality and KZ. So K dot S prime minus X is here. Okay, so exponential terms comes with this one. Wow, looks complicated. Yeah, I agree, very complicated. We can use the Bezel function identity. Bezel function identity means exponential term can be expanded into a Bezel function, and this one times exponential terms. So this one can be rewrite into this equation, and this one, another one, this one is here. So exponential term here can be decomposed into sum over 2, the product of 2 Bezel function with the same argument. Same argument. One is S, the other is S prime. Okay, sum over X. Sum over X. And here we have a common terms, omega. A common terms, omega minus K Z V Z minus X omega alpha. Okay, let's relativistic effect. Before that, without magnetic field, we do not have this term. But here, with the magnetic field, we have extra terms. These terms are quite common for magnetic field, for magnetized plasma, like electron sectron measure, like fusion. Okay, quite common. How about X? S is sectron harmonic. Sectron harmonic. Okay. Actually, for a magnetized plasma, this is very important terms, extremely important terms. Just like relativistic Doppler shift under magnetic field. Okay, so what else? If we want to calculate this one, we need to calculate this term and just substitute to here and substitute everything to here. So eventually, let me skip this part. Our purpose is to calculate here these terms. One more time. The mathematical detail can be calculated if needed. My experience is most of the students, master students, or even the undergraduate student have the ability to derive this equation by himself. If I give him some example. Okay. Okay, therefore, I don't worry about the derivation. And you don't have to focus on the mathematical detail. Just have a look at this equation, and you know how to derive this equation when you need. Okay, let's move on. Have a cup of tea. Move on. So we can rewrite this equation. Our purpose is here, shown here. We can carry out the tau integration, perform the integration, and we obtain this equation. This can be found in the curl of and a trivial piece. In the curl and trivial piece. The Bezel function has the same argument here. Okay. Looks okay. And the conductivity tensor, sigma, the conductivity tensor, if you remember, conductivity tensor, sigma, we already assumed the conductivity tensor. Now let's derive this tensor starting from the very beginning. Okay, we derive this tensor. We know J is related to this one, and we will sum over all the particles, all the species. So substitute this one. We have F1K, and F1K, what else? This one, we have, for example, the X component is here. We use V perpendicular and phi and Z. We separate into this one, 3 variable, not S, Y, Z, but this one. We do that because we want to simplify the integration, not Vx, Vy, Vz, but V perpendicular. And then we will derive into X component. This one depends on this one and this one. Okay, so sigma xx is the coefficient of E1kx terms. Therefore, sigma xx can be obtained into here. Don't worry about the mathematical detail. Don't worry. So by substituting everything into here, we got sigma xx is here. That's the coefficient. Okay. How about sigma xy and other 8 components? Okay. Sigma xx. Finally, the general dispersion relations can be expressed as this form: dxx, dsy, dxz, dyx, dyy, dyz. These two are axisymmetric. What else? Others are by similar method. We obtain the other element of the dispersion tensor. We define an other factor, chi alpha. Chi alpha will be shown later. In addition to chi alpha, we have lambda alpha, chi alpha, chi alpha, chi alpha. Okay. By similar method, we obtain the other element of the dispersion tensor. So that's all the elements. F alpha, this is not the dispersion function, distribution function. No, it's a new definition. And X alpha, chi alpha, lambda alpha is shown here. Page 35. Lambda alpha, chi alpha. Okay. Now let's consider the waves propagating along B0 directions. Wave propagating along the B0 directions. So wave number will be in a K direction. We will separate into, today's course separate into 2 parts. Have a 10 minutes break and we will be back. Okay, let's stop here.